Good morning. Can you guys hear me okay? Is it on? Is this thing on? Good morning. All right, thank you guys for joining us today for our seminar. Today we're really fortunate to have Stephanie Smallegan. She's a new faculty at the University of South Alabama. Is it working? Can you hear me? All right. She's a new faculty at the University of South Alabama. She started in August of last year. She's in the Department of Civil and Coastal Engineering. And today she's going to spend a little time talking to us about daily and storm surge related processes. She uses numerical models to understand how this affects shorelines. She came to us from Virginia Tech, where she got her PhD. And she told me she also has a slide where she's going to tell us a little bit about herself, so I'll stop talking so she can do the rest. Thank you.
Thank you. All right, good morning, everybody. I have already been in class once today, so I've got my voice turned on, which is why the microphone was a little low. I purposefully named my title very vague in hopes that I would get a good turnout, and I got a great turnout. But I put some buzzwords up here: coastal resiliency, developed barrier islands, and today I do want to make the distinguish between a developed barrier island, like much of Dolphin Island, where we've got buildings and infrastructure, and an undeveloped barrier island. So I'll be focusing on the developed ones. All right, that about me slide. I did go to Georgia Tech for my undergrad and master's, but I never stepped foot on the Atlanta campus. I was actually at the Savannah campus, much like this one. It has just a few buildings, really tight-knit group, mostly driven by the grad program there. Graduated with my master's in 2012, and my master's work was day-to-day processes. We were looking at Cape Hatteras, North Carolina. Anybody been there? Couple people. Anybody ever climbed the lighthouse? Couple people in Cape Hatteras? I had a key to it for a whole month doing work there, as an undergrad actually. But anyway, so I was looking at these long-term processes along Cape Hatteras, lots of field work involved with that, decided for my PhD that I was going to completely switch gears so I could be a very well-rounded coastal engineer. And for my PhD, I started looking at barrier islands and how they're destroyed or damaged during hurricanes. So that will lead you up to today, where now I'm an assistant professor at South Alabama in the Civil, Coastal, and Environmental program there. And I was technically started in January as an instructor, but have been the assistant professor since August. So if you've heard my name for a little while now, then that's why. All right, brief introduction. Most of you know about barrier islands, and most of you know about hurricanes and how damaging they can be. But I did want to give you this slide just to refresh your memory, and to also orient you for the rest of my talk. This is a schematic or a cross-shore profile of the barrier island, a barrier island that I'll be talking about. So this is an actual profile from my study location. In my talk, the ocean will always be on the right, and the bay will always be on the left. And there are a few things that I've listed in here that are characteristic of most barrier islands. We've got a dune, may or may not have a berm, and we've got this back barrier, it may or may not have buildings. So I wanted to go ahead and point that out to you so that you can kind of see what this upcoming slides are going to hold for you. When we're looking at storm impacts, we can classify those in regimes based on their severity. Going from panel A to B, C to D, these are becoming more severe. This gray shaded region will be your initial profile before the storm happens, and then the black will be the final profile, so to speak, after that regime has been met. So the swash regime, I'll use this throughout the talk also. It means that we've got some processes going on, some morphological change or some erosion at that berm face. As the storm becomes more severe, we're going to enter the collision regime, which means that our berm is now completely eroded and we're starting to eat away at the dune. And then we can move into the overwash regime. This is where you start getting into a lot of damage. So I'm in panel C now. The overwash regime is where we have an eroded berm. Our dune is partially destroyed. The dune heights have been reduced quite a bit. And then the one that causes the most damage is this inundation regime. The study location that I'll show you goes through all of these and ends in this inundation regime. This is where we end up with a breach. You've probably heard of a breach. So we have Katrina Cut that happened nearby, right? That was this inundation regime. So the inundation regime can completely destroy buildings, and it can cause new inlets to form on barrier islands. So how do we protect them? How do we increase our resiliency? Well, civil engineers in all of our infinite wisdom, we've come up with about 2 or 3 ways to do this. One is nature-based. We can put more sand on the beach, but then there's some issues with that. We got to continue to do that, right? It's not a long-term fix. We can try hard structures, but there's some issues with those too. They're not really that pretty, right? So we've got Galveston, Texas, who they put a seawall up. It has greatly increased their resiliency, so to speak, but they have no beach access. There's no beach there. This is pretty bad for tourism. So a compromise, taking the best of both worlds, would be to combine those two. We can then have a buried seawall, for instance, beneath a dune. So we'll have our hard structure. We'll put some sand on top of it, which is what you're seeing here. This was a seawall that was uncovered during Hurricane Sandy, which happened in 2012. And I'll talk more about Sandy, I believe, on the next slide. But this is a rock seawall that was buried underneath a sand dune. And as the storm passed, then the sand was eroded, the seawall was exposed. This is an example of a combination nature-based and hard structure. If you're looking at these, we're talking about beaches, dunes, structures underneath the dunes. But what about Bayside Hydrodynamics? Usually we say oceanside, that's where our energy is, it's causing most erosion, so forget about the Bayside. We want to protect against ocean surge and waves. So this is a topic that I really want to look into. How important are those Bayside hydrodynamics? To answer that question, let's look at a case study. And this is what my PhD work was on, Hurricane Sandy. If you remember that timeline that I gave you of the about me, I started my PhD the year that this hurricane made landfall. And I wanted to switch my focus from long-term processes, so that's day-to-day conditions, to short-term processes, storms. And this happened to be a storm of record for this location. This thing's beautiful, right? I mean, it's affecting the cloud patterns over here by us. It's a huge storm, impacted half of our country, everything from wind and hail and tornadoes and flooding to blizzards that happened in West Virginia and a couple other states. So if we look at Hurricane Sandy's path, which is given on this map by the dashed line, then we see where it made landfall, and I've got a little arrow pointing towards Bayhead. Bayhead, tiny little town on a barrier island in New Jersey. I've zoomed into that location on the right. And just below Bayhead, less than 2 miles apart, is the city of Mantoloking. And if you think back to 2012, we saw pictures of damage, a breach that had occurred in Mantoloking. That was a breach in the barrier island. There was a bridge that had been destroyed. You may have remembered that one. That was this location in Mantoloking. So we're looking at Bayhead, 2 miles south, Mantoloking. They experienced the same storm forcing but had completely different a response to the storm. What we thought might have happened was a seawall that was buried in Bayhead protected that borough or that township. So what I'm going to talk about is this seawall in Bayhead for the rest of the talk. To give you an idea of the difference in damage between Bayhead and Mantoloking, I grabbed some Google Earth images. The pre-Hurricane Sandy picture in the middle shows a nice sandy beach. And on the right, we have this rock structure. And what's really cool about this structure is it was originally built in the late 1800s. And the residents in this town of Bayhead, they're so transient that most of them didn't realize the seawall was even there. So when they're finally able to return back to their homes, they're like, yay, my house is only flooded. It's not completely destroyed. But now, instead of having oceanfront property, I've got this rock seawall where my beach used to be. And it had some of the locals wondering, what is going on? Why is this here? I didn't put it here, and it wasn't here before. What we had to do when we went into do our field survey at this location was tell them that this may have actually been what saved your home, and that's what we're going to try to find out. So if you talk to your neighbor down here in Mantoloking, their houses were destroyed by this breach. This is just one of the smaller ones, actually, but it's so close to the location of the seawall that we found it pretty interesting. Before we did any kind of numerical modeling work, we wanted to look at how many houses did the seawall possibly save, and what was this damage. So our first assessment was looking at Google Earth imagery, just like I showed you, and classifying each house as either flooded, damaged, or destroyed. Every house on the island was flooded. So that was pretty easy. Damaged and destroyed was a little bit more difficult to discern. Damaged, we said maybe the roof line changed, maybe we could tell from the Google Earth imagery that a porch had fallen off or whatever the case may be. But destroyed was the house is no longer there, or the house looks like it's no longer on its original foundation. We did see houses that were seemingly picked up and moved. Yeah, it was crazy looking at this data. So the map on the left shows Bayhead. There's a red line that indicates the location of the seawall. The little black dots are high water marks. And we included high water marks on this figure because we wanted to show that they're basically the same between Bayhead to the north and Mantoloking to the south. That means that the storm forcing between these two locations was about the same. But then if we move to this panel C, then in Bayhead, lots of flooded houses, very few damaged, very few destroyed. In Mantoloking, however, lots of destroyed houses. So this, again, led to that hypothesis. What did this seawall do? Because this is cool, right? We found that something we hypothesized it was the seawall reduced damage from 56% down to 12% at this location. To test that hypothesis, we decided to go to numerical modeling, which is where I've come into play. So I used the numerical model XBeach to perform this work. XBeach is fantastic because it is designed to model those regimes, the swash, collision, inundation, and overwash regimes that I talked about before. It works excellently for complex bathymetry, like developed barrier islands. You're able to actually put structures on the beach. They can't be destroyed, so every model has its limitations. This one has quite a few, but it's excellent for this work because you can have those structures and it can model storm impacts very well. Day-to-day conditions is not so good with that. But for what we're using it for, excellent model to use. Model setup. If any of you are modelers, you know that this is one of the hardest things to do, create a grid with the most up-to-date data. So we have lots of different data sets that fall into our model grid. The full grid is shown on the top. We use only the portion that's in the rectangular box, or the rectangle. That area alone was used for our analysis. And that is a very high resolution, about less than a meter resolution in that box. And the dashed dot line through that rectangle is a cross-shore profile. I'm showing that on the bottom. So again, just as I showed you before, ocean is on the right, bay is on the left. The spikes in the data are the buildings. And if I zoom into the dune and berm area, then this triangular looking dotted line, that represents the buried seawall. So in these simulations, we ran half of them with the seawall to represent Bayhead and half of them without the seawall to represent Mantoloking. That's our model grid. Hydrodynamics, we used, again, lots of different data sets. We had instrument failure quite a bit with Hurricane Sandy. So we had to grab the most accurate data that we could from all kinds of different sources. But what we ended up getting was at our X-Beach boundary, at the offshore boundary, we had about 8-meter waves. It's pretty big. Period corresponds to swell, and the period was almost shore normal throughout the peak of throughout the storm duration. That's the boring stuff. The really cool stuff is this panel D, the surge. The ocean surge, we have, our tides, we reach a peak, but look at the bay surge. The bay surge almost looks like a tsunami, where we have a recession of water, and then it rushes back up, and it jumps up by almost 2 meters at this location. When we did our field survey, the locals said that you could sit and watch the water levels rise, that it was so drastic throughout that day. Well, we thought that might have an issue or a part to play in all of this. So we broke up our modeling results into 2 phases. Phase 1 is prior to that huge rush of water in the bay that's characterized by large waves and ocean surge. Panel A shows you with the seawall. Panel B shows without the seawall. And we see a few differences. So this is the morphological change. And if we compare the two at this time, then the seawall, we're already seeing the dunes are weakened a little bit more than the seawall location. We have almost a little, don't want to call it a breach, but we've got some channelization of flow around this building, one of the buildings, and that's causing quite a bit of erosion right there at the dune. Are y'all ready for this? I'm ready for this. Phase 2. All right, if we look at panel D, it looks a whole lot like panel A. If we look at panel E, it doesn't look anything like panel B, right? So B and E comparing the island topography at these different snapshots in time, and this shows that panel B and E show that without the seawall, we have a whole lot of erosion that's happening during phase 2, not during phase 1, where we have high ocean energy, basically ocean waves and surge, but during phase 2, after we have that huge rush of water in the bay. That's interesting. Well, why did that happen? The first thing we wanted to look at was, well, what about the seawall? What did it do? What were waves doing? You know, since it is oceans, we tend to think that they're most energetic. What you're looking at here is a plot of wave energy. This is a little bit difficult to grab in a presentation without studying it, but on the y-axis we have landfall day. -1 means 1 day prior to landfall, 0 means Hurricane Sandy made landfall, and then +1 is 1 day after landfall. What this shows, panel A on top, is that initially we've got high wave energy. It erodes the dune. And then about at landfall day 0, the seawall's exposed, and it's preventing that wave force from propagating further onto the island. So we have no waves at all on our island. And the seawall location is indicated by the vertical dash line. Now if we go to panel B, that's the no seawall case. We see the same process happening. We have dune erosion starting to occur around -0.5 landfall day. And it continues to occur until landfall, but then after that, the dunes are completely eroded away, and we have a very small, but we have some wave energy that's on the island because we're looking at a location that a breach occurred, right? So that's wave force, but that doesn't really tell us anything about our morphological change. This morphological change could be caused by the waves here, maybe not. They're really small, they're there. So what we did instead was looked at delta Z. Delta Z is the change in our topography. The blue represents negative numbers. That means we've got erosion. Red would be accretion. In panel C, this is just behind the seawall. We notice that at landfall day 0, we've got just a tiny bit of erosion happening. But then look at panel D with no seawall. We see we've got some erosion at landfall day 0. But then we've got this huge erosive event that happens at the peak of bay surge. So that was really interesting. And if you take the integral of both of those, then we can look at wave force in that area. We see that the wave force in the no seawall case is twice as big as the seawall. And we also can very clearly see that in the absence of a seawall, our erosion becomes much greater when the bay surge rises. So it really turned into a two-step process. Yes, the dunes had to be weakened by ocean surge and waves, but then the damage that we saw in Mantoloking, these model results indicate that that was actually caused by this huge rush of water in the bay. Well, then what happens if we change that? And that was the next step. So let's look at, instead of just what Hurricane Sandy did, what happens if we shift that bay surge? What happens if it happens sooner or later than when it actually happened with Hurricane Sandy? And then what happens if we increase and decrease our magnitude? This led to a hypothesis of increasing magnitude will increase our erosion, that will increase our damage. That makes sense. But we really didn't know what to expect with this time shift. First, I'm going to give you some qualitative results. Again, this is seawall versus no seawall. Panel A, again, boring, right? The seawall seems to protect its island. The only time that we see more erosion in the presence of the seawall is if we increase surge magnitude by 50%. Well, of course we do, right? That makes sense. But then look at panel B. Without the seawall, 50% is the only time that we end up seeing more erosion. Otherwise, the erosion is relatively reduced, especially near the dune. So that means that this first building, that oceanfront building, that one may have actually even been saved if our bay surge profile had looked a little bit different or had occurred at a different time. So let's look at the quantitative. This is a beautiful black and white graph, right? Not a whole lot of color, but it still has a profound impact. We can look at sections of the island. The top, A and D, show the island as a whole, and we're looking at volumetric erosion. The equation is given here at the very top. So we're looking at volumetric erosion over the course of the entire storm. How much erosion did we actually see under each of these conditions? A and D are the erosion on the island. B and E are the erosion on the dune. And then C and F are the erosion just on the back barrier. So we were able to divide the island up into different locations or different areas. In all cases, what we see is that this no change condition in C, that's Hurricane Sandy conditions. And unless we increase our surge magnitude, that was our worst case scenario. So this led us to believe that Hurricane Sandy, the bay hydrograph, the bay surge that was generated by Hurricane Sandy, was the worst possible scenario that could have happened in terms of our timing. Obviously, if we increase our magnitude, then we saw more erosion. We could shift our bay surge back by 3 hours, so that huge rush in bay surge could have happened 3 hours sooner. That's right here in the middle of the graph on the left. And we still would have seen a significant reduction in our volumetric erosion. If we want to use volumetric erosion as a proxy for damage, perhaps the damage wouldn't have been as much with that negative 3 hour shift either. So these are the quantitative numbers. This one's really interesting too. If we look at the time evolution, so the previous slide just gave you how much erosion happened on the island throughout the storm. This, what you're looking at here, is again given by landfall day, and we've got volumetric erosion on the island, dune, and back barrier again. This is the seawall case only. And what we're looking at is the volumetric erosion that happens under each of these conditions throughout the storm duration. This is the seawall case. Again, not a whole lot going on, right? We have erosion starting to happen quite a bit before the Hurricane Sandy actually makes landfall, around maybe 0.25. If we increase our bay surge magnitude, then we see an increase in erosion, especially on our back barrier, about the time that the bay surge jumps up and increases. But now if we look at the no seawall case, then we see that the morphological change that happens on the island then is very correlated with our bay surge hydrograph. And this is for all cases, except for this negative 6 hour shift. But if we look at an increase in magnitude, or a decrease in magnitude even, or the no change, the actual Hurricane Sandy conditions, then again this is pointing towards the fact that the erosion happened on this island and the damage was as bad as it was because of Bayside Hydrodynamics, not necessarily by the ocean surge. These results also show the benefit that the seawall likely had on this island, according to these model results. So in summary, seawall seemed to make a difference, at least for this location in the storm. There are lots of limitations to this study. Can we really use volumetric erosion as a proxy for damage? That's an area of future work. And is a seawall on your barrier beach always a good idea? Not saying that either. So don't go building seawalls everywhere based off of Dr. Smallegan's talk. But then we also see that Bayside Hydrodynamics can play a huge role in our morphological change, a process that we, at least as engineers, we tend to kind of brush off and say, well, we know that the surge is going to increase in the bay, but we're worried about the ocean side. I don't know that we can necessarily write that off anymore. So I've included some future work here, including vegetation on the island, maybe building up our model so that it can actually destroy buildings. But the big one at the bottom, what does this mean for Alabama? And that's exactly why I was so excited to come here and talk to you today, because this is my area of expertise. I'm looking to move this down here to Alabama. I'd love to talk to some of you that are interested in research, collaborating with me on this. But, Dauphin Island has been one of those target areas for me. What happens if we model this area? Are there ways to prevent a Katrina cut from happening? That kind of thing. And what are the processes behind those morphological responses? So with that, I will take any questions